Hello, we're Senior Design Team Litterally Trash, the IEEE Robotics team. Our project was to construct an autonomous robot capable of identifying, collecting, and dispensing litter. The competition consisted of multiple rounds with a 12x12 arena containing 4 types of litter: aluminum cans, plastic bottles, chip bags, and paper trays. Cans and bottles can be placed in a metal or plastic bin respectively, while chip bags and paper trays must be dispensed in trash bins only. The ultimate goal of our project is to combat the persisting problem of pollution.
Pollution is an everlasting problem in the modern world. As cities expand and population grows at a rampant pace, pollution grows as well. So in order to keep up with expanding pollution, some cities have implemented semi-automated trash handling services. However, the end goal is to design and build a completely autonomous system using object detection and all-terrain mobility to handle trash.
The IEEE Region 5 organization provided a document containing the specifications that our robot must follow. First, the robot must operate autonomously, including navigating the playing field and identifying, collecting, and dispensing litter for 2-minute rounds. Each robot must conform to the following size constraints. The robot must fit in a 2 cubic feet volume of space, must not weigh over 25 pounds, and it must not contain any hazardous components or materials.
High-level architectural design here with all the different layers. The controls and communication layer is the central, most important layer, and it functions as the brain of our robot, processing the data received from all other layers. The detection layer consists of all the environmental input devices and computer vision software, while the movement layer deals with the mechanisms related to navigation. To finish it up, we have the collection and dispensing layer to elaborate the picking up, storage, and dispensing workflow.
The Jetson Nano was chosen as processor for its low power, low cost, good reputation, and many resources online that we can work with. It supports Ubuntu and ROS. The base of the robot is a wooden board, 12 inches by 23 inches. While not as strong as metal, wood is much lighter and cheap in weight. Wood is also much easier to cut, allowing us to run wires through and make small changes when needed. Originally, we were planning on using a metallic robotic kit. However, it was too costly and weighed much more than the wooden base.
So our collection mechanism is composed of a spinning brush made out of 3D printed bars that hold these brushes. The length chosen was 18.5 inches, and this allows for support and motors to hold and spin the brush and allow enough length to pick up trash. And our dispensing and collection unit is made of a cardboard box which holds all the trash collected. This box is connected to 2 motors that spin the box upward and dispense the trash into trash bins located behind the robot.
We used a Logitech C270 HD webcam and a TensorFlow SSD MobileNet object detection model to detect trash items. A MobileNet is a lightweight network that helps complex machine learning algorithms like SSD to function on resource-constrained devices like Raspberry Pis and Nanos. A LiDAR assists the robot in its tracking its location relative to the arena. The initial and target locations can be identified, and a SLAM algorithm helps to map and navigate the field.
We prototype calculations for brush lengths of 19.5 inches and 16.5 inches, finally settling on 18.5 inches. This proved highly effective in picking up all types of litter. The robot's 6 inches diameter wheels allow for enough lift to move all the circuitry of the hardware and the undercarriage of the base, giving the cardboard bin rotation space to freely move without the risk of damaging any hardware components. We did 20 test rounds and were able to collect around 16 pieces of trash per round.
The IEEE Region 5 conference laid out the specifications that our robot must adhere to. We successfully implemented our design under the weight and size constraint, as our robot weighed in at 22 pounds and fit perfectly inside the 2x2x2 foot area. We quickly learned that the best material to build with were simple wood and cardboard, which were light and cheap to make. Other materials like aluminum and acrylic are heavy and require special tools to shape to our needs. We learned to keep it simple and cheap, otherwise it would defeat the purpose of the robot. Our biggest requirement was making the robot autonomous. We settled on having the robot start at an initial point and move to a target point using a SLAM algorithm and dispense, rather than the robot process its environment through the computer vision depth maps and calculate its own path. While that would have made our robot more dynamic, it would have became too complex to implement with the online transition. Code for controlling motor controllers was provided by Chris Colander, which allowed us to focus on calibration and scripting movement with the motors instead of making everything from scratch. Future plans include odometry with computer vision to enhance the autonomous navigation. Sorting the litter items by using a partition container and object detection will also prove effective for recycling.